Wow, looks like we got a pretty big crowd. That's pretty cool, but that also means that I think there's a lot of people that think my talk isn't going to suck. So let's hope I live up to that expectation. Looks like people have kind of recovered, or at least gotten up and going after last night's pretty awesome party. I'm especially excited to see that a bunch of the BT guys made it after we shared a few beers together. That was pretty cool. We still have a few more people filtering in, but I've got a lot of material to cover, and I'm going to kind of have to move through it pretty quickly. So I'm going to go ahead and get rolling, but don't feel bad about shuffling around and finding your seat. Okay, my name is Zachary Cutlip, and I'm going to be talking to you today about reverse engineering and exploiting the BT Home Hub 3.0b. And I'm a senior vulnerability researcher at a company based in the US called Tactical Network Solutions. And at TNS, I spend most of my time researching and developing exploitation techniques targeting embedded systems and network infrastructure similar to the Home Hub and other devices like that. So what's the point of this talk, or what's the focus? Primarily, this talk is focused on my investigative process as I was investigating the Home Hub. And I'm going to talk about things that I tried and strategies that I pursued that didn't necessarily work out or yield a lot of fruit, but I thought were interesting nonetheless to talk about. And of course, I'm going to talk about how I ultimately succeeded in finding a vulnerability that I was able to exploit and gain root on the Home Hub. This talk is less focused on O-days and exploits. There are a lot of talks that are where the speaker is going to drop an O-day or something excited like that. I actually released this vulnerability publicly earlier this year. So the vulnerability itself is not news. And as it turned out, BT in their own research had found the vulnerability independently of me. So as I mentioned earlier, I'm going to be really blasting through a lot of material. I'm going to have a lot of screenshots of code that I'm not going to spend a lot of time on. I'll trust that if you are interested, you'll go back and look at the slides later to have a closer look at that. And also there's a white paper. I'm not sure if that white paper has been made available to you by the conference, but even if it isn't, I will share a link to my white paper that you can download. And it's got really a ton of information. It was very difficult to condense all that down into a bunch of slides. So there's a lot of information in the white paper. Okay, that said, here's a picture of the Home Hub 3.0b, and my understanding is this is actually one of the most widely deployed SOHO routers in the UK. So it should be a fairly familiar sight, and I actually have one with me today. So it should be a somewhat familiar sight. Here's the back with the typical assortments of ports where you have a broadband port, number of switched Ethernet ports, USB port, what have you. The Home Hub 3.0b is manufactured by Huawei, but to say it's made by Huawei is somewhat of an oversimplification, because as is the case with a lot of these embedded devices, the chipset manufacturer actually does a lot of the engineering and a lot of the hardware engineering, and actually develops a large portion of the SDK. So the chipset manufacturer in this case is Broadcom. Here's some additional kind of geeky details about the Home Hub if you're interested. And in particular, I want to call out the fact that we're running Linux, and in particular, a really old Linux kernel, 2.6.30. And that's useful to know for a couple of reasons. One is, from an analysis perspective, many of the things that you're already familiar with in terms of interacting with the Linux system are going to be applicable to this system. Also, many of the advanced protection mechanisms that come into play in Linux kernels don't come into play until later kernel versions than what we've got here. So for example, we have an executable stack, and the stack on this system is randomized, but nothing else is, so there's no ASLR in the libraries or heap or anything like that. When you log on to the web interface for the Home Hub, one of the things that you find is actually relatively limiting in terms of how you can configure it compared to offerings from third-party vendors like Linksys and whatnot. And in particular, one of the things that's worth noting is that this device can only connect to the internet via PPPoE, and it can only accept, the web interface will only accept credentials that are issued by BT. So there's really no way that I'm aware of to connect this device to any other internet provider. From a firmware perspective, unlike devices from third-party vendors, there's no firmware, there's no vendor website where you can go and download a firmware. And even if you had a firmware file, there's no facility in the web interface to upload a firmware update. So the firmware is completely managed by the internet provider. So the backstory behind how I came to be researching this device, there were some users on the forum.kits.co.uk forum who wanted to hack their home hubs, and basically they wanted to unlock some additional configuration capability. And one user in particular emailed me, and he had seen me on the Hack5 podcast talking about researching and exploiting Netgear devices. He emailed me and said, hey, you know, we're working on this home hub thingy. Would you be interested in joining in on the effort? And I said, well, okay, if you ship me some hardware, I'll take a look at it, but no promises. And I sort of thought that that would be the end of the story, and I would never hear from him again. And as it turns out, he came through and shipped me a couple of home hubs across the ocean, and so that was kind of cool. So I got the hardware, and with the hardware in hand, I logged onto the forum to see where we were on the research, and it turned out another user on the forum had already desoldered the flash chip and extracted the firmware, because, like I said, you can't download the firmware. And so with the firmware extracted, that gave us a really valuable beachhead on beginning to analyze this device, because there's no way to interact with it dynamically and get root on it to analyze it that way. So you've got to start with a firmware and do some static analysis. So that was super cool that the firmware had already been obtained. So the overall goal in the project was to unlock the Home Hub, make it more configurable, maybe find a way to connect it up to another ISP, and possibly even upload a custom firmware like DDWRT to it or something like that. My immediate goal was to get root, okay, because I need to dynamically analyze this device. There are some questions that you simply can't answer from static analysis alone. Like I said, you can't get root. There's no serial port that I'm aware of. So we're going to have to find some kind of vulnerability that I can exploit and get root on there. Then I can get a debugger on there. I can enumerate processes, things of that nature. And I'm looking for as easy an exploit as I can find. I don't care if it's behind an authenticated web page. I do not care. I just want to get root, and I don't want to spend a lot of effort doing that, because once I get root, that's when the real research hopefully will begin. So I'm really looking for low-hanging fruit. So my investigative process basically involved a breadth-first approach, which is what I think a lot of people will tell you. You don't want to pursue any one strategy too far and too deeply, only to find out that that strategy isn't paying off and yielding any fruit, and then you've got to completely back up and start over again with a new strategy. And you just don't, you don't want to get bogged down on one thing and kind of get tunnel vision. And I'm known around the office to get frustrated when a strategy isn't working out and I can't get tools to work right, or things just aren't going my way, basically to proclaim hacking is bullshit, right, and just like stomp out of the office. And when that happens, it's time to back away from what I'm doing and then come back and try a different strategy. And maybe, if necessary, circle back and revisit some things that I've already looked at and got frustrated with. So that said, the attack surface that I investigated on this included the web interface, which is arguably the most attractive attack surface in that it is the most user-facing and in many ways the most complex attack surface. I also investigated UPnP. There are actually 2 UPnP services running on this device. I investigated the USB port, and if I understand correctly, I believe in a previous version of the Home Hub there was a vulnerability such that you could plug in a specially formatted USB drive and gain access that way. I investigated the PPPoE client. As I mentioned, this device only connects to the internet via PPPoE, so I was able, and it only connects to BT. I was able to get a PPPoE server to masquerade as a BT backend and accept BT credentials. So I thought that would be kind of an interesting attack vector if I could get in that way. And I spent quite a bit of time investigating the configuration backup file, which in theory represents a number of interesting attack vectors, and I'll go into that in detail in a bit. The first class of vulnerability that I looked for was a command injection vulnerability, and this is actually a really common class of vulnerability in Soho routers. We come across them all the time, and usually we find a command injection and then that's it. You know, we're done. We can move on to some other device. It generally consists of some sort of unsanitized input from the user, usually from the web interface, that is turned into a command that will be executed by the shell by passing it to the system function or popen function, something like that. They're nice vulnerabilities because they're relatively easy to discover. Just some strings analysis on your binaries oftentimes will turn one up. And if you find one, they're pretty easy to exploit, right? You don't actually have to do a lot of debugging, really easy. Sometimes you can just pass like a reboot command in, and it's immediately obvious if the vulnerability worked, right? Because the device reboots. In addition to that, they tend to be very portable. So let's say you have two similar devices from the same manufacturer and the same bug is in the firmware on both devices. Oftentimes you can use the exact same exploit code on both devices without refactoring it, even if they're running a different CPU architecture, because you're really just relying on the underlying commands that exist on the system. On the other hand, since you are relying on the commands that exist on the system, if there aren't any useful commands, then a command injection can be pretty limited. And I have seen devices that even though they run Linux, they don't even have basic utilities like chmod or chown or things like that. So you can be somewhat limited by a command injection. So here's an example from a different device, and this is the kind of thing that we look for right out of the gate. And what we have here is actually a really common pattern. Let me explain what's going on. Oftentimes the router will have a diagnostics page. Oftentimes that page is unauthenticated. And what it does is it causes the router's web server to execute a ping, and you give it the IP address or host name of a server to ping, and then the router can verify whether or not it has internet connectivity. And then your input into the web page is usually sprintf'd into a buffer, so that's kind of nice. You often usually have a buffer overflow there to go as well. And then that command is passed to system and executed by a shell. And so then in the web interface, if you entered something like google.com /sbin telnet-d, it would, in addition to pinging Google, also start up a telnet server. So then you're in like Flynn. So to look for one of these bugs, like I said, oftentimes it's just a matter of doing some strings analysis and just looking for strings that look like they would be executed by the shell. And then if you find some, you need to verify which if any of those are actually passed to a shell and which are combined with user-supplied input. On the home hub, there is an executable called CMS that gets executed by the web server a bunch for a number of different reasons. And the CMS executable itself executes lots of commands. And among them are IP tables commands. And IP tables is one of the ones that I often look at because the portion of the web interface where you configure port forwarding rules, oftentimes that input to the web interface is getting transformed into an IP tables command. So if that's not being sanitized, then you may have a command injection vulnerability there. So here's an example where I'm looking for IP tables commands that look like they're being passed to a shell. And I found a bunch, actually. I found about 189 of these strings that look like system commands. And one in particular stood out that I thought was a really nice one to talk about. And among other things, it takes 12 different input strings, right? So this is a printf style format string that takes 12 different input strings. And I thought there's no way out of these 12 strings, at least one of them is not from the user, okay? The chances of none of these strings being from the user seem small. And in addition to that, it's got this shell style redirect, right? I mean, that's a really unique syntax. The shell style redirect is born shell syntax. So I'm certain we've got a string that's going to get turned into a command that's going to be executed by the born shell. At this point, I basically was ready to call it a day and just go home because I had found what I was certain was an exploitable bug. So I just need to run it to ground. So do we have an actual command injection vulnerability here? Well, is there unsanitized user input? That can be a little hard to verify, especially if the input is passed off through multiple functions and maybe even through multiple processes. It could be sanitized or mangled in some way at any point along the way. So that can be a little tricky to be sure of. So an easier question to ask is, how does this command actually get executed? Is it in fact passed to a shell? I mean, it certainly looks like it is. Here's a disassembly fragment of how the Home Hub executes commands, or how the Home Hub's web server executes commands. And I'll explain what we have going on here. So first, a command string is generated by snprintf, which in and of itself is actually a little unusual because many times we see, like I said, a command string being generated by the comparatively less safe sprintf. After the command string is generated, it's passed to a function called qosexec, and then qosexec passes the command string onto a function called atputilexec command no hang. So how does atputilexec command no hang work? That becomes a question that we need to answer. So when I disassembled this function, what I found was really things other than what I expected. So to start with, it parses this command string into an array. Well, that's a little unusual. Then that shell redirect that I was certain was a win, it means this command is going to be executed by a shell, it actually opens that file that was referenced by that. Okay, well, that's weird too. So then we get a fork, not what I was expecting. Then that file that got opened gets dupe2'd, so standard out or standard error gets dupe2'd onto that file that got opened. Then we call execv on our command array, and then we call wait for that process to finish. Well, that was disappointing too. So basically at this point, what I found is that even though we had what for all the world looks like a command is going to be executed by the Bourne shell, we don't actually have a Bourne shell, which is sort of the magic component that we need. So basically means no easy command injection here. That was pretty disappointing. I did find one function called atputilexec command, which does execute the Bourne shell, but I was only able to find very limited use of that command, and near as I could tell, it didn't take any unsanitized user input. So this is one of those points where I had put a lot of time, really more time than I wish I had of, and I need to back away and come up with a new strategy. So the next best thing to look for is buffer overflows. And in the world of SOHO routers and embedded devices, even some pretty nice commercial embedded devices, it's almost like we live in an alternate universe where it's still 1996 and no one has read Aleph 1's seminal stack smashing paper and everyone is still using strcpy, strcats, sprintfs, and things like that. And when we find all these, there's tons of opportunities for exploitation there. So going back to our previous example, remember I said we had a command injection, but if you were feeling kind of badass and didn't want to take the easy way out, you've also got a buffer overflow here with this nice sprintf. That's the kind of thing that we're looking for, and I find them all over the place. Sadly, I didn't find them all over the place in the Home Hub. I actually found a limited or no use of those functions. The few uses I was able to find, I was able to track down and verify they weren't being used unsafely and being used with unsanitized input. There were a few exceptions, but unfortunately those programs that had uses of those dangerous functions were pretty difficult to analyze, at least statically. They didn't disassemble cleanly, and they were pretty frustrating to analyze. So I ended up leaving them and coming back multiple times, and kind of trying something else and then coming back. So I'll talk about those exceptions in a bit, but the short story is I wasn't able to find any really easy buffer overflows. So once again, it's time to find a new strategy. So one of the things that I probably spent the most time on, basically because I thought it was pretty interesting, was analyzing the configuration backup file. And the configuration backup file, like I said, represents a number of potentially interesting attack vectors. First of all, it's generally trusted, and it's assumed to be unmodified from what was generated by trusted code, which means that if we can tamper with it in some way, we might be able to violate some of those assumptions. So it's assumed to be well-formed, so if it isn't, we might be able to find some sort of memory corruption bug that we can exploit, like a buffer overflow. Sometimes you'll find that the configuration backup file, when you restore it, is actually parsed under the hood by a shell script, which may be an opportunity for a command injection since it's very difficult to sanitize input in a shell script. Additionally, there may be options in the configuration grammar that are not exposed in the GUI. So for example, there may be undocumented backdoor creds, there may be some way to turn on some kind of admin interface in the configuration file that you couldn't get to in the GUI, so maybe an SSH server or something like that. So the configuration backup file is usually obfuscated in some way, and this is generally for tamper resistance. And I think generally the case is that the vendor kind of doesn't want you dorking around with it or it becoming damaged in some way and then bricking your device and you calling technical support. It's usually encrypted in some way, either via some well-known encryption mechanism or some homegrown custom encryption mechanism. In addition to being encrypted, it's often signed to further make it tamper resistant. If it is encrypted, and it's a custom encryption mechanism, oftentimes the developers of the mechanisms are not mindful of proper cryptography principles. And it may be a simple matter of reverse engineering the algorithm and re-implementing it, and then you've got a tool that can encrypt and decrypt the config file on your own. On the other hand, if they're using a well-known cryptography algorithm, cryptography implementation. If the algorithms are sound and the keys are well protected, you're not likely to find a weakness there. At least you're not likely to find a weakness that someone else hasn't already found. There are a lot of smart people hopefully looking at these cryptography mechanisms. And what I found when I disassembled the configuration import-export API was that the Home Hub is using AES. And I thought, well, AES is certainly well understood. It's well respected. I assume they're probably using like per device keys or something like that. And I almost didn't analyze it. I was like, it's not going to be worth me finding a bug in AES or trying to find one. So I was like, this isn't worth it. Then I thought, hold on a second. If I backed up my configuration from my Home Hub and then it broke and I needed to get a replacement and the vendor sent me a replacement, I should be able to restore that configuration file. And so I had a couple of Home Hubs and so I tried it and it worked. And so what this meant to me was that every Home Hub, at least that's the same model, has everything that it needs to decrypt another Home Hub's config file, which means that the firmware that I downloaded from the forum also has everything that it needs to decrypt a config file. So I decided it was worth looking at after all. So I spent some time reverse engineering the configuration import-export API, and I found that the configuration configuration backup starts out life as XML, and then it's compressed with the Unix gzip command, and then it's AES encrypted, and then base64 encoded, and then it has a 128-bit AES signature prepended. I don't know why the signature is not signed and then base64 encoded, because you end up with this like 16-byte chunk at the beginning that isn't base64, but nonetheless, that's what happens. So we have a disassembly here of how the config file is restored, and I'll explain what's going on here. So first, the Home Hub verifies the signature and then removes it. So we have the signature removed from the configuration file. Then it base64 decodes it, and then it decrypts it, and then it decompresses it with gunzip. And it's actually a relatively straightforward API. And so you can write a little C program that just calls the import function and pass it the name of the file, and it will decrypt it for you. And in fact, I don't even care about checking the signature, so I was able to skip that part and actually just remove the signature myself and then pass it the base64 encoded file. So I wrote my little C program and cross-compiled it and ran it in QEMU. I linked it against libcfm API, which has the API in it. And I ran it in QEMU, and I ran into some interesting problems. This was almost comical. What I found was that there were a number of functions that the dynamic linker couldn't find. So things like PZMM kfun2. That's pretty weird. It's weird in a few ways. For one thing, most of the functions and libraries on the system sort of conform to a predictable namespace. So the functions will be generally named for the library that they're found in. There was no library where PZMM kfun2 appeared to belong. So the linker couldn't find these functions. I was able to do some strings analysis and track them down in the libraries they were found in, and they were just sort of found all over the place in random libraries that appeared to have nothing to do with configuration, import, and export. And it turns out that PZMM kfun 1 through 4 actually build an AES key 4 bytes at a time just by poking one byte at a time into an array. And in PZMM ifun 1 through 4 build an AES initialization vector, again by poking constant values one at a time into an array. So I found those functions, and I was able to use LD preload to get the respective libraries loaded up. And I ran my program in QEMU again, and this time I had success, and it decrypted my configuration, which arguably is the first actual success that I've had so far in this project. So here's a fragment of the decrypted configuration file, and we can see it's XML data with a bunch of router settings in it. So the next step was to basically reverse the process and see if I could modify the config file and then re-encrypt it and sign it and then upload it to the home hub. And so I tried that, and it worked. So I'm able to make some changes to the file, upload it to the home hub, and it takes my changes. So again, more success. This is starting to feel pretty good. It's about time. So while I was at it, since I had a program that I could run in a debugger, I went ahead and ran my decryption program in a debugger, and I snagged the AES key and initialization vector out of memory. Partly just because it's cool to snag someone else's AES key out of memory. Also because it let me write a standalone program that I didn't need to link against the configuration API. I didn't need to cross-compile it then, and I had a native program that I could use that would encrypt and decrypt the config file. Also, if you know a little bit about encryption, which is basically what I know, you know that the initialization vector shouldn't be constant. So that's kind of interesting. We have a constant initialization vector. I don't think this is a real problem because, like I said, the goal is most likely to keep the encryption file from being tampered with. So, I mean, there aren't super sensitive secrets being protected here and being transmitted across an unsecure medium, but that's kind of interesting. Okay, so with the configuration file decrypted, I was able to do some strings and look at the XML elements that were in the encryption in the configuration file and do some strings analysis on the configuration import-export library, and so kind of infer the XML schema that the configuration file should conform to. And basically, what I found is that there weren't any XML elements in the configuration file that weren't also in the library and vice versa. So the API isn't looking for elements that it didn't find in the configuration file. There also weren't any things in the configuration file that weren't already exposed in the GUI. So sadly, we have a pretty good representation in the GUI of what we have in the configuration file, which means that there's not a lot we can diddle with there. Before I gave up on this, I did have a look at the default configuration. So there's this file called defaultconfig.xml on the router's file system. And the same trick basically applies to it, and you can decrypt it. And when I decrypted it, I found a ton more options. And there are some remote admin creds that I assume are used by the ISP to remotely administer the device. But I did find that it was a very different schema from what was in the backup configuration file. So my attempts to modify it and restore it in place of a backup configuration file or steal some of the XML elements out of it and put in that backup config were not successful. So it was disappointing. Spent a lot of time on this strategy and had some successes, but ultimately didn't meet the goal I was going for. So it's time to revisit some things that I have looked at previously. And like I mentioned before, there were some programs on this system that had abundant use of sprintfs and strcopies and whatnot, and I kept coming back to them. I mean, it's like a siren's call. And every time I would come back, I would find that they were just, I couldn't get anywhere from static analysis. There were functions that had no cross-references to them, so I wasn't able to figure out a code path to get into those dangerous functions. There were lots of jump tables. There were lots of really enormous case statements, so it's kind of a mess to disassemble. So I really wanted to be able to run it in a debugger. So I'm going to need some dynamic analysis. So I'm going to need to go to QEMU, and I've got I've got a tutorial on my blog on getting Debian MIPS Linux up and running in QEMU, which I use all the time. And I just SSH into my Debian QEMU machine, and I've got NFS, and it mounts my workspace inside Debian. It's pretty neat. So if you want to know more about that, that's on my blog, and I'll share this link again later at the end of the talk. So if you miss it, don't worry. So the program that I'm looking at is called BCM UPnP, and it's a UPnP server whose job it is to manage the wireless hardware on the home hub. And this program is actually provided by Broadcom. The problem is I couldn't get it to run in an emulated environment. It makes a lot of assumptions about the hardware that's present. And of course, Debian MIPS Linux isn't going to satisfy those assumptions. It also makes lots of queries to NVRAM for configuration data, and you're not going to have NVRAM in Debian MIPS Linux. So getting it going turned out to be a lot of work. That's why one of the reasons I left this piece and came back to it multiple times. One of the things I ended up doing was basically write a faker library that would intercept calls to NVRAM get and provide answers. And you basically provided an INI style configuration file and hopefully make some sane guesses about the settings that should be found in NVRAM. And you can check out my library if you want from my GitHub repo. And again, I'll share this link at the end of the talk. So with NVRAM solved, I was able to get BCM UPnP up and running, but it would just idle. If I would send imp searches to it, it wouldn't respond to them, which basically means we're going to have to go back and do some more static analysis and figure out what's going on there. So getting pretty frustrated yet again. Like I said, I left this piece of the project multiple times and came back to it. So what I basically found after a lot of reverse engineering was that when BCM UPnP has no wireless hardware to manage, it just ignores imp searches, all right? So it turns out there's a global structure that has a couple of fields that get modified when the program starts up and doesn't find any hardware. What I ended up doing was basically binary patching out those modifications. And I'm not completely clear what this structure does or what the modification, what values are being set there, but I could tell that if those values got set, then it wasn't going to respond to imp searches. So here's a before, and here's an after where I had knocked out where it's storing those values. So with that modification made, with NVRAM faked and with the binary patched, I was able to get BCM up and running and finally responding to imp searches, which means that I can start tracing some code paths that I think lead to dangerous functions. When I did, I pretty quickly found a nice store copy that if in an imp search packet, if you put a UUID in the search target, it'll store copy the value of the UUID onto the stack. That's pretty nice. And if you provide an excessively long string in place of a legitimate UUID, it'll crash the program. So here we see BCM UPnP looking for the UUID string in the search target, and if it finds it, jumps down here to this stir copy. So I basically wrote some Python code that would generate an imp search packet. I put my buffer overflow there in the search target, and when I fire that at the home hub when I fire it at BCM UPnP running in a debugger, I get this nice crash. So we basically, at the end of the function, jump to code that I control. Sweet. Now this is the kind of success that I've been looking for. So at this point, I just want to kind of make an aside and talk for a second about Bowcaster, because Bowcaster is a project that evolved out of my home hub research and some research into some other devices. And basically, when I and my colleagues first started researching Soho routers and exploiting them and exploiting buffer overflows, what we found is that there were a number of things that we sort of had to figure out from scratch, right? So if you're exploiting buffer overflows on x86 or ARM smartphones, there are a number of exploit frameworks that sort of have you taken care of and provide, payloads and whatnot. But for MIPS Linux, there were a few things out there, but it didn't work very well. The stuff that was in Metasploit didn't work at all. I was able to find some shellcode on the internet that kind of worked, but it wasn't reliable. So I ended up developing a lot of exploitation techniques on my own, targeting embedded devices. So I ultimately rolled all that into a framework that I call Bowcaster. It's really lightweight. It's written in Python. And it's basically an API. I mean, it's got a number of things in it, but it's an API that lets you describe your buffer overflow in a really modular and organized way. So you can describe where all the ROP gadgets should go, tell it where the payload should go. You've got a number of MIPS Linux specific payloads that I've written for it, and a number of other useful utilities. It's got some connect back servers, so then, rather than using stupid netcat where you can't remember the syntax because there are like 8 different versions of netcat with different syntaxes, there's a connect back server that you can use right in line in your code and use it programmatically. So anyway, so there's some neat stuff in Bowcaster. I'm pretty proud of it. And if you want to check out Bowcaster, here's my GitHub repository. And like the other links, I will share this link again at the end of the talk. So I've got my crash. Now I need to develop my exploit. And like I said, it's an imsearch packet, right? So it's a single multicast packet with the buffer overflow. Developing the exploit was a lot easier with the tools that I got in Bowcaster than it would have been otherwise. I was able to finally get a root shell via one of my connectback payloads that I've written. And I tested and developed the exploit against BCMU PNP entirely in QEMU, right? Because I'm not able to get on this device and dynamically analyze it and use the debugger. So I had to rely entirely on emulation. And then when I tested it against the home hub, I got root on, is my slide not loading? Crap. I got root on the first try. And that was actually pretty cool. Because what that means for us is that in theory, we don't ever need the actual device. All we need is the firmware to find a vulnerability, develop an exploit. And that's cool because there are a ton of Soho routers out there. I can't order them all from Amazon and analyze them. We can order some of them and then maybe return them, saying they're defective because we found a vulnerability. But there's still just too many routers, too many embedded devices in the world to analyze. So if you can do your development and testing and emulation and have an exploit that you know works, that's pretty cool. Okay, so if you want to have a look at the proof of concept exploit code, here's my GitHub repository where you can have a look at that. And there's some other exploit code in there for some other devices. But that said, now it's time for what arguably is my favorite part of the presentation. So we're going to do a demo of the exploit. So demos are my favorite part. I love popping root. I love seeing other people pop root. It's just a lot of fun. So it kind of went a little crazy. And I also wanted to showcase some of the stuff I can do with Bowcaster because, like I said, I'm pretty proud of it. So rather than just using my basic connectback payload that'll pop a shell and then we have root and then a second later we're done, I'm using a different payload that I wrote called Trojan Dropper, which basically will connect back and then we'll download a stage 2 payload and execute it. And then that payload will connect back and download a rootkit that I put together and then drop it on the file system and then pop me a root shell. So you can see here, this is a stage 2 payload that it's going to download, assuming everything works. This is my rootkit that it's going to download and drop on the file system. And it's going to drop it in /temp because /temp is in RAM. The rest of the file system is not writable. So I'm going to run the exploit, and it's a live demo, so you know how things go, but hopefully we'll be lucky and it'll work. So it printed out the buffer overflow to the screen. It's waiting to send my stage 2. It sent it. It's waiting to send my rootkit. It sent that, and now we have root on the home hub. We see we're running Linux. Here's the rootkit, so I'm going to go ahead and unpack that. Fortunately, this device has a lot of useful Linux commands on there, so I'm able to rely on things like tar. That's nice. So I'm going to install it. And I kind of bundled a couple of things into here. One is I compiled a copy of BusyBox that basically has like all of the options turned on. And like BusyBox is kind of one of those utilities. I think BusyBox by itself probably meets like half of what I need out of a Linux distribution. It's got so much in it, so that's pretty cool. In addition to that, I hacked up I hacked up the Dropbear SSH server, which turned out to be really challenging to get running on a wireless router for reasons I can talk about offline. So my script has installed my special copy of BusyBox. It's installed and started up my SSH server. So I'm going to go ahead and be brave and kill my shell, and then SSH in. And the SSH server is nice for a few reasons. One is the connectback shell is a kind of a crummy shell, right? It's not an actual terminal. And so if you do Control-C, it kills your shell. You don't have command history or tab completion or anything like that. Also, it's in the clear, so if you're doing this remotely and you don't want anyone to see what you're doing remotely, the connectback shell is not great for that. SSH is good for that. So now we're in via SSH. I don't kill my shell. I've got command history. I can cd into my tk directory, and there's BusyBox with all my tools turned on. Basically, all of these nice programs on here are symlinks to BusyBox. So we've got a pretty nice working environment. So if you're an attacker, that's pretty cool. But also if you're just a researcher, right? We want to get on here and dynamically analyze it. Now we have lots of tools to work with. I can put a debugger on here and just go to town. So I've got a really good working environment. Okay. That said, like I said, the demo is my favorite part. And it kind of went a little crazy. So I took the liberty of bringing a couple of additional home hubs with me. And like I mentioned, this is it's a multicast exploit. So any device that you have on your local Ethernet segment who is subscribing to SSDP multicast should be able to see your exploit, right? Which means that all three of these home hubs should see the single exploit packet that I'm going to send out. And you might think, well, that's kind of contrived, because who's going to have three home hubs on one network? Well, what if it's some other device that is subscribing to multicast rather than a router? So maybe like a bunch of wireless net cams. You don't even need to enumerate what all devices are on there. You just lob your exploit, and everyone who gets it is going, if it's vulnerable to that exploit, is going to be exploited. And then you'll know how many devices are on the network. So I wrote a server for Bowcaster that is basically it's a multiplexing connect-back server. And it will receive multiple connections, and each connection that it gets, it will farm out to another connect-back server. So I've got these three connect-back servers waiting to give me shells, and then in this terminal, I'm going to run the exploit and have my multiplexing connect-back server hopefully, keep my fingers crossed, receive all those connections. So let's run the exploit. I've got a different version of it, and actually I'm going to just make sure they're all up and running and receiving and responding to M searches, and they appear to be. Okay, so now I'm going to run my exploit and keep my fingers crossed. Well, two out of three fired. This is always disappointing when I'm going to give it a go again. I would say about, and I'm not really sure why, but I would say about 1 in 10 times, one or more of them misfires. But I think it's worth giving it a try again. I think I'm doing okay on time. How are we doing here? Waiting for all the lights to turn blue. Okay. Almost. We have all blue. Let's make sure that they're responding to M searches. Incidentally, this is a tool written by my colleague Craig Hefner called Miranda, and if you want to poke around with UPnP and do some enumeration and do some things that normally you wouldn't be allowed to do, you can use Miranda. And I just fire up Craig's tool and run M search, and I see all the responses come back. Miranda is actually a pretty useful tool. This is unbelievably disappointing. Are we good, or? I think that was just the alarm that means this exploit better damn work the next time. What's that? Okay. Unannounced test. Excellent. Best kind. Okay. Okay. Well, I'm going to try it again. And if it works this time, it works. If it doesn't, at least we tried. All right. This time we got root on all 3 devices. We got a call from 254. Got a call from 252. And from 253. So you can actually see, the traffic going by here in my multiplexing server. Anyway, okay, enough playtime. Almost done. Thanks for being patient while I diddled around with the devices. Okay, okay. So that said, so we have root. Really, we're still not done. Unfortunately, we still don't have an unlock for the Home Hub 3B, at least that I know of. The first thing I did after getting root on the device was remount the root file system writable, because it's JFFS2, and you can do that. And I made a trivial change. I touched a file or something, and then rebooted it, and it bricked it, right? So it actually boots up with a red light blinking, and it's in this recovery mode. And it's got a web server listening, and presumably if I had a firmware update file, it would accept that firmware update file to recover it. I don't have a firmware update file, so I need to get one somehow. Also, assuming I can recover it, I'm going to need to find some way to evade that integrity check on the file system, either by figuring out how to recompute the hash of the file system or just evade the check altogether by maybe patching the bootloader or something like that. Additionally, the Home Hub 4 is out now, and I have a Home Hub 4, but I only have one. It's got this tiny little flash chip on there that looks like it's going to be a pain in the butt to desolder, and of course, my device will be bricked at that point. And also the flash chip is a little BGA chip. I don't have the gear to deal with the tiny little BGA flash chip, so I haven't touched my Home Hub 4. All right, just quickly, I want to give some acknowledgments to Craig Hefner, my colleague, who's taught me everything I know basically about researching and exploiting embedded devices. My company, TNS, who gives me time to work on projects like this. William Kirby, the forum user who shipped me the hardware initially. AsboKid, the forum user who extracted the firmware and gave us that beachhead that was really cool. Also, Scidoc.com user D. McDonald shipped me some hardware, and that was really great. Here is a link to my blog that has a list of all the resources that I've talked about in the talk. So rather than just giving you a whole ton of links to write down, hopefully you can just go to this blog post and find everything you need, including a link to my white paper. And someone let me know if you want me to put that back up again. If you want to talk to me, I love talking about this stuff. So email me, get in touch with me on Twitter. I'm on Twitter quite a bit, and then here's a link to my blog as well. So that said, if you want to talk to me now, I think we have time for questions. I love questions. Oh, okay, there's one.
So were you breaking into this from the internet side or from the home side or either?
So for the exploit, for the vulnerability that I found today, this is a LAN side only vulnerability. The UPnP server is not exposed to the internet. When I was looking for vulnerabilities, anything was fair game because I just wanted it on the device one way or the other. Going once. Is there a hand I'm not seeing? Going twice. Okay. Well, I appreciate everyone coming out, and I enjoyed talking about it. Hope you enjoyed it too.